Welcome everyone to this demo on how to run FMI-based co-simulations using the INTO-CPS application. This demo is given in the context of a tutorial that is to be held as part of the International Modelica Conference in October in Aachen, Germany. I am one of the organizers. I am Claudio Gomez, and I am one of the organizers of this tutorial. We will start by downloading and installing the INTO-CPS application and checking that we have the right environment to avoid problems. First, if you open a terminal, for example PowerShell, you should check that you have Java installed. So if I type Java version, you should get something that looks like this, and note that this tutorial is being carried out using OpenJDK version 11. So if you have problems and you suspect they are caused by a mismatch in the Java installation, then make sure you have version 11. To download the INTO-CPS application, you can just Google INTO-CPS application, and you should find either the GitHub page or the INTO-CPS page. And on the GitHub page, you can go to the releases and download. This is where we keep the source of the application. If you download the latest application for your platform down here, in this case we're going to download this executable. If you wish to install the application, then you can download the setup, but in this case it suffices to just execute the executable. After you download this, you will have it on your downloads. Double clicking on it will open it, and if you have worked previously on projects, then it will open any previous projects you have worked in. In this case, I'm starting from a fresh setup, so I don't have any projects that have been previously opened. Now we need to download another tool that we use, a download manager in the INTO-CPS application to download it. So if you go to Window, Download Manager, and select the latest release, you should then see a list of tools that can be downloaded that are compatible with the latest release. In particular, we're interested in downloading this co-simulation engine. This is a tool that the INTO-CPS application will invoke when running an FMI-based co-simulation. Confirm that you wish to download. Yes, now the download has been made. By default, the downloads are made into your Documents folder. And here you can find INTO-CPS projects, install downloads, and you can actually see COE jar. So this is a command line application. It has a web application interface, and that is used by the INTO-CPS application to communicate with it. But you don't have to worry about any of those details. After you have downloaded it successfully, we can now start creating a project. And we'll give it a name, for example, into demo. You select where is that project going to live in your file system. So in this case, we can put it in our downloads folder. I'll just create a folder here for demo and select this folder. And now you should see I have it on my downloads. Then I press create. It should create the default structure of a project. If you visit your downloads folder, you should now see this is the default structure of the project. And you can see we've got the location, the folder where the FMUs should be, as well as the folder where the multi-models and configuration of the co-simulations will be, which we will start filling in soon. The last thing to do before moving to our next part is to check that the COE can be initialized. And so this will use your Java installation to launch the COE. So if you press launch here, this is the command line argument used. So if you have problems, you can always try it from the command line. And if all goes well, you should see this online green part and a bunch of info log messages. So we are ready to move to the next part. The next step is to locate the FMUs that are going to be used to run the code simulation. In this case, we have them in our downloads folder. These are the 3 FMUs, and we are going to copy them or move them into our project folder FMUs. And they now should be visible in the INTO-CPS application interface. So now the next step is to create a multi-model, which is a description of the FMUs, their instances, and how their instances are connected. So I can right-click on the multi-models and select New Multi-Model. We are just going to leave the default name here. And there's nothing yet. We will start filling it in. So we edit the configuration. We add an FMU, and we will add each of these FMUs. So the first one will be called controller. The path is controller inside our demo folder. You should see that it is supported. It means the FMU contains binaries that are compatible with your platform. We now add the drive FMU following a similar procedure, and the stimuli FMU. Okay, all 3 FMUs are added. We can close this part. Now let's create instances. We have 1 instance per FMU. It is possible to have multiple instances per FMU, but in this case we only have 1 instance. I'm just giving them smaller names. I'll call this input. Okay, so we have 3 instances, 1 per FMU. Now we're going to connect the instances. So the controller instance has an output variable v, and it should be connected to the drive input variable v. So this is the input variable of the drive FMU that is now connected to the output variable of the controller FMU. So the control connections, the connections between FMUs are made from left to right. The drive FMU has an output variable w, and the controller will receive that value. The input FMU has 2 output variables, the load torque, that is going to the drive instance, and the W desired, that is going to the control instance. Right, the connections are made. Now we have to create parameters. In this case, we do not wish to change any of the default parameters of these FMUs, so we're not going to add any parameters here. We can save, and now on top we can see an overview of the outputs and the corresponding inputs. So an overview of the connections between the instances of the FMUs. And this is our multi-model. Next, we create a co-simulation configuration. So we right-click on the multi-model and we create a co-simulation configuration. This is because we can have multiple co-simulation configurations per multi-model. In this co-simulation configuration, there's a number of configuration steps we need to take. So we edit, there's some default settings. In this case, the demonstration is from time 0 to time 1 second. Our algorithm, this is the kind of orchestration algorithm we will be using. It can be variable step size or fixed step. In this case, we will use the simple fixed step, which means the FMU instances will communicate every 0.001 seconds. So there will be 1,000 steps being done in this co-simulation. Visibility, this has to do with whether we wish to enable logging or debugging stuff. So we're going to leave the defaults here. Stabilization, this has to do with handling algebraic loops. So it's not something we are going to deal with here. This is to create plots. What do we wish to see during the co-simulation? in this case, we are going to add a graph, and here we can say we wish to see the variable w and the w desired. So we wish to see them in the same graph, and then we can add a new graph where we wish to see the controller output, for example. So we have two graphs being created. We can configure all connected outputs are going to be saved by default in a results CSV folder. You can additionally, if there are particular other outputs that you wish to plot as well, to record as well, then you can select them here. In this case, we do not need to select them. And there are some other options, such as we can slow down the co-simulation to real time, or we can use parallelization. None of these are relevant now. You can also run a particular script if you wish to carry out some task after the co-simulation is done. So we save. We have already launched our co-simulation orchestration engine, and so we do not need to launch it again, but if not, then there will be an option here to launch it, and we can press simulate. And we are done. You can see here the W desired and the W coming out of the drive instance. And as you can see, the controller is doing a decent job at ensuring that the drive is following that similar, that desired W. You can also see the V output of the controller here. If you open the results folder, you can access the CSV files, which you can then use to create better plots or to carry out other subsequent analysis. The results folder, so just to show you, this is our demonstration project. If you go into multi-models, you can find the multi-model we created here. And in this multi-model, you can find a JSON configuration that really represents the connections. That represents the connections, the FMUs, their instances, and how they're connected. So the same information that we've produced in the user interface. And then we have the co-simulation configuration here, which is this one. That contains again another configuration file representing our co-simulation configuration. You can see the description of the plots here, for example. And you can see the results folder. As you see here, you can see the results of your experiment that are time-stamped by the time you started the experiment. And here you can see the configuration files used. This is because we can change the configuration file as we are running new experiments. So each experiment, the results are recorded with the configuration that was used to generate those results. You can find a zip file with logs from the different FMUs, should you wish to carry some debugging. And here you can find the outputs CSV file, where all the results in the simulation are available. In this next part, we'll create alternative co-simulation configurations and show the relationship between the communication step size, the co-simulation step size, and the results. So we will right-click again on the multi-model and create a co-simulation configuration. Maybe we'll give it a different name. We will open it and we will now edit the basic configuration again. 1 second, fixed step size, and now instead of using the step size 0.01, we will just use the step size 0.05. So we are increasing the step size. We will plot, nothing to change here. We will create a plot. We will just plot the W against W desired, and everything else remains the same. So then we simulate. And the results so far, they look good. So let's try increasing the step size again. To 0.01. Okay, they are starting to look a little bit jagged. Let's increase the step size some more. Okay, and now the results don't make any sense. Let's see if we can locate the step size that's somewhat breaking point. Okay, yeah, the results here, they start to look very different than what we've seen before. So this is probably the absolute maximum step size we can use. And this is because the FMU instances are communicating less often, which means that in between time 0.05 and 0.07, for example, there is no communication between the FMU instances. So they are probably assuming that the inputs are kept constant in that interval. And even if they are using extremely accurate numerical solvers inside the step of the co-simulation, the fact is that their inputs are very outdated. And this leads to instability in the results and inaccurate results. So it is very important in general to try running the simulation with different step sizes to understand how robust those results are with respect to changes in the step size. For example, if I go to 0.01, I'm getting pretty good results. If I go to 0.01, I will have a much slower simulation. Okay, now I cannot plot the entire plot because I'm getting too many steps, so it's showing me a limited window. But we can configure that in here to use a different graph sampling interval, a larger one compared to the step size. So before we were actually using, this should work. Yes, so now we are seeing the results are not changing fundamentally from our previous results using the step size 0.01, which indicates that we are in a safe interval of step sizes for this co-simulation. This concludes our demonstration. We have seen how to download and run the INTO-CPS application. We have seen how to create a new project, how to import FMUs into that project, and then how to create instances of those FMUs and connect them, as well as how to run co-simulation by creating a co-simulation configuration. And then we've also seen how to analyze the impact of the step size in the co-simulation results.